There's a moment at the start of everything, a before and after, and the space between them. For our universe, that moment was the Big Bang, the beginning of time and space as we know it, an explosion of energy so immense it gave birth to galaxies, stars, and the very fabric of reality. But what if I told you that those earliest instants, those first chaotic seconds of creation, left behind a kind of cosmic fingerprint, not something we can see, not something we can touch, but something we can feel, in a way, through the language of gravity itself? These are the primordial gravitational waves, the universe's first ripples in the fabric of space-time, echoes of the birth of everything. They carry with them secrets from a time before light, before matter as we know it, from the very edge of what we can possibly understand. Think about that for a second. The idea that the universe didn't just begin in a flash, it rang like a bell, sending vibrations across reality that are still traveling, still whispering to us across billions of years. These ripples aren't just some abstract idea, they're real, physical undulations in the cosmos, stretching and compressing space itself as they pass through. Detecting them would be like hearing the very first note of existence, a direct message from the moment of creation. And what's even more thrilling is that scientists around the world are racing to listen, to decode what these gravitational waves are trying to tell us about how it all began. In this video, we're going to explore 30 incredible theories about these cosmic echoes. Some are grounded in our best current physics, others float at the edge of imagination, proposing ideas that challenge everything we thought we knew. From multiverses to hidden dimensions, from the nature of time to the possibility of other universes brushing up against our own, each theory opens a door to a deeper understanding of not just where we came from, but what reality truly is. So join me on this journey. Let's dive into the echoes of the Big Bang and uncover what the universe's first whispers might be trying to tell us. Our first theory takes us back to that unimaginably brief sliver of time, a fraction of a second so small it's almost poetry. This is the era of cosmic inflation, a concept proposing that the universe didn't just expand after the Big Bang. It exploded in size faster than the speed of light, doubling and redoubling in an instant. Picture a single subatomic particle suddenly swelling to the size of a galaxy in less time than it takes to blink. This wasn't a violent explosion, but a smooth, incredibly rapid stretching of the very fabric of spacetime itself. And it's within this frantic stretching that our first ripples are thought to have been born. How does stretching space create a gravitational wave? The answer lies in the quantum world. Even in what we might think of as a perfect vacuum, empty space is never truly empty. At the tiniest scales, it's a seething, bubbling foam of quantum fluctuations, where pairs of particles and antiparticles spontaneously pop into and out of existence. During the calm periods of the universe's history, these fluctuations are small and localized, but inflation acted like a cosmic amplifier. As space expanded at a phenomenal rate, it grabbed hold of these minute quantum jitters in the gravitational field itself and stretched them across the cosmos, freezing them into reality and magnifying them from the quantum to the cosmic scale. What started as a tiny, microscopic quiver was inflated into a massive, macroscopic ripple in the fabric of space-time, a primordial gravitational wave. These waves are not like the ones we detect from colliding black holes today. They are a permanent background hum, a fossilized imprint from creation, crisscrossing the entire universe. And this is where the theory offers us a way to potentially detect them. These primordial ripples would have left their mark on the oldest light we can see, the cosmic microwave background radiation. Think of this radiation as the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. As these gravitational waves moved through the infant universe, they would have slightly polarized this light, creating a distinctive, swirling pattern known as B-mode polarization. Finding this specific pattern in the CMB is like finding the signature of inflation itself, a direct fingerprint of those first moments. It's a whisper from a time before atoms, a message written in the geometry of the universe, waiting for us to learn how to read it. But if inflation was the amplifier, our second theory introduces a different kind of instrument altogether, one born from a crack in the very symmetry of the young cosmos. Picture the universe cooling from its initial, unimaginably hot and dense state. As it cools, its fundamental forces and particles begin to settle into the forms we recognize today, much like water freezing into ice. But sometimes when water freezes, the process isn't perfectly uniform. Defects can form cracks or fissures trapped within the ice. According to this idea, the early universe might have undergone a similar phase transition, and in doing so, it could have created its own kind of cosmic defect. Not a crack in ice, but a flaw in the fabric of spacetime itself. These hypothetical structures are known as cosmic strings. Imagine a cosmic string not as a thread you could hold, but as an infinitely long, incredibly thin filament of pure energy, thinner than a proton but with the mass of a mountain range packed into every mile. They are essentially one-dimensional wrinkles in reality, relics of a time when the laws of physics were settling into their current form. If they exist, these strings would be under immense tension, causing them to vibrate at nearly the speed of light whipping through the cosmos. And just as a violently plucked guitar string sends vibrations through the air as sound waves, an oscillating cosmic string would send violent vibrations through the fabric of spacetime itself, generating powerful, distinct gravitational waves. The signals from these strings would be unlike any other. While the waves from black hole mergers are transient bursts, a network of cosmic strings would produce a continuous background hum of gravitational radiation, a permanent choir of these cosmic vibrations. But even more distinct would be the occasional spectacular event. When a cosmic string loop oscillates, it can eventually reach a point where it pinches off and dissolves into a tremendous burst of energy, emitting an incredibly sharp, singular burst of gravitational waves, a cosmic shout against the steady hum. Detecting such a burst would be a smoking gun, a clear signal that cannot be easily explained by any other known astrophysical phenomenon. The search for these signatures is already underway, with astronomers using pulsar timing arrays, networks of incredibly precise, rapidly spinning dead stars that act as cosmic metronomes. As a gravitational wave from a cosmic string passes through, it would minutely disrupt the perfectly timed ticks of these pulsars. By monitoring an array of them across our galaxy, we are effectively building a galaxy-sized gravitational wave detector, listening for the telltale hum or the sudden, sharp burst that could finally confirm the existence of these bizarre, ancient scars on the face of the universe. Finding one would be more than just a discovery. It would be a direct glimpse into the processes that shaped the fundamental forces moments after the birth of everything. But to find a different kind of cosmic vibration, we must look to a process not of stretching or snapping, but of boiling. Our third theory takes us to another pivotal moment in the universe's infancy, a time when the cosmos underwent a dramatic transformation in its very nature, a process physicists call a phase transition. We see phase transitions all around us, water turning to steam or freezing into ice. The early universe experienced something profoundly similar, but on a scale that defies imagination, as the fundamental forces of nature themselves began to differentiate and separate from their initial unified state. Picture the universe in its first moments as an unimaginably hot, dense, and perfectly symmetrical soup. All the forces we know today, gravity, electromagnetism, the strong and weak nuclear forces, were merged into a single, unified superforce. But as the universe expanded and cooled, it reached a critical temperature where this perfect symmetry could no longer be maintained. It was a cosmic version of supercooled water, which remains liquid below its freezing point until a single impurity triggers a sudden, violent snap to ice. In the universe, this snap was the separation of the forces. This didn't happen smoothly everywhere at once. Instead, the transition began at random points where tiny quantum fluctuations provided that initial impurity. At each of these points, a bubble of the new, broken symmetry phase of the universe nucleated and began expanding at nearly the speed of light. Now, imagine these bubbles forming in a roiling sea of the old, symmetric universe. As they expand, their walls race outward, and when two of these incredibly energetic bubbles finally collide, the impact is catastrophic. The collision sends a tremendous shockwave rippling through the fabric of spacetime. Furthermore, the entire process is one of incredible turbulence. The expanding bubbles stir the primordial cosmos into a frenzy, much like a pot of water reaching a rolling boil. It is within this chaos, the violent collisions of bubble walls, and the intense turbulence they create, that powerful gravitational waves are generated. These aren't the gentle hum from quantum fluctuations. These are shouts from the death throes of the universe's symmetric past, a series of violent events that sent powerful ripples across reality. The fascinating aspect of this theory is that it could have happened at different energy scales, depending on which specific force was separating. A grand unification phase transition, where the strong nuclear force split from the electroweak force, would have occurred at an almost inconceivably high energy, producing the most powerful gravitational waves. Another transition, when the electroweak force itself split into the electromagnetic and weak forces, would have created a different signature. Each of these events would have imprinted a unique frequency and amplitude onto the gravitational wave background. This means that by searching for these waves across different frequencies, we are not just listening for a single note, but potentially tuning into an entire symphony of cosmic phase changes, each movement telling us about a different chapter in the universe's first second of existence. Detecting this signal would be like finding the geological record of the universe's most dramatic growing pains, a direct testament to the moment its fundamental rules were set in stone. Our fourth theory ventures into the realm of the profoundly dense, proposing that the universe's first instance might have been filled with the birth and death of the most enigmatic objects in the cosmos, black holes. But these wouldn't be the stellar mass black holes we know today, formed from the collapse of giant stars. These would be primordial black holes, forged directly from the extreme pressures and densities of the Big Bang itself. Imagine patches of the newborn universe so incredibly dense that they didn't expand with the rest of the cosmos. Instead, they simply collapsed under their own immense gravity, punching a hole through the fabric of spacetime in the process. These objects could have been virtually any size, from smaller than a proton to many times the mass of our Sun, all forming in less than a blink of an eye. The gravitational waves from these ancient objects could have been generated in two spectacular ways. First, consider their formation. The actual collapse of one of these ultra-dense regions would have been a violently asymmetric event, a catastrophic crunch that would have sent powerful ripples through the surrounding spacetime. The universe's first second would have been filled with the ringing of these birth cries. But the second, and perhaps more significant source, would have come later as these primordial black holes began to interact. Drifting through the dense early universe, they would have been drawn to each other, colliding and merging in cataclysmic events that would make the black hole mergers we detect today seem tame by comparison. A merger between two primordial black holes would unleash a torrent of gravitational waves, a distinctive signal echoing from the dawn of time. This theory becomes even more compelling when we consider one of astronomy's greatest mysteries, dark matter. We know it exists because of its gravitational influence on galaxies, but we have no idea what it's made of. What if a significant portion of dark matter isn't some exotic particle, but simply these ancient primordial black holes? They would be invisible, yet would exert exactly the kind of gravitational pull we observe. If this is true, then the early universe would have been teeming with them, making collisions and the resulting gravitational waves incredibly common. This leads us to a key difference in the signals we might detect. The gravitational waves from modern stellar mass black holes, like those detected by LIGO and Virgo, fall within a specific frequency range that our ground-based instruments are tuned to hear. The waves from mergers of much larger primordial black holes, however, would have a much lower frequency, creating a constant background hum that could be picked up by space-based detectors like the future LISA mission. Furthermore, mergers of very low-mass primordial black holes would produce high-frequency signals, a kind of cosmic chirp that would require entirely new types of detectors to hear. Finding this chorus of waves across a vast spectrum of frequencies would be the clearest evidence that the early universe was a chaotic arena where black holes were born not from dying stars, but from the raw energy of creation itself. Now we pivot from the fiery birth of the cosmos to a theory that suggests our universe wasn't born from a single, solitary explosion at all, but from a collision. This is the ekpyrotic universe theory, a profound alternative to cosmic inflation that draws its name from the ancient Greek word for conflagration, or out of fire. It proposes a far more majestic and cyclical origin, one that plays out not in the three spatial dimensions we experience, but within the mind-bending framework of string theory and its hypothetical higher dimensions. To grasp this, we have to step into the world of brains. In string theory, a brain, short for membrane, is a dynamic object that can exist in multiple dimensions. Our entire universe, with its 3 dimensions of space and 1 of time, could be just one such 3-dimensional brain floating within a higher dimensional expanse known as the bulk. Imagine our universe not as an isolated bubble, but as a vast flat sheet, like an impossibly thin slice of bread adrift in a higher dimensional loaf. Now picture another brain, a parallel universe, floating on a parallel course in this same higher dimensional space. The ekpyrotic model suggests that our universe began when our brain and this other one collided. This wasn't a destructive crash, but a transformative event. The immense kinetic energy of that impact was converted into the matter and radiation that filled our newborn cosmos, creating what we now perceive as the hot, dense state of the Big Bang. This elegant idea completely reimagines the beginning. There was no singularity, no moment of infinite density. Instead, there was a collision, a defining event that set everything in motion. But the theory doesn't stop there. It proposes a cyclical model of existence. After the collision, the 2 brains bounce apart, driven by the force of the impact. They then drift through the bulk, slowly drawn back together by a faint attractive force over trillions of years, only to collide once again and spark a new Big Bang, a new cycle of creation. In this view, our universe has no true beginning or end, only an eternal rhythm of collision, expansion, and rebirth. This radical shift in origin story leads to a crucial and testable prediction about gravitational waves. In the inflationary model, the quantum fluctuations that get stretched become gravitational waves with a very specific signature. Their strength is predicted to be roughly the same across all wavelengths, creating what physicists call a scale-invariant spectrum. But the ekpyrotic scenario paints a different picture. The process of a brain collision is much smoother and more gradual than the violent, exponential stretch of inflation. It doesn't amplify quantum fluctuations in the same chaotic way. Consequently, the model predicts that the primordial gravitational waves generated would be incredibly faint, essentially negligible. The signal would be orders of magnitude weaker than what inflation theories suggest. This creates a clear observational fork in the road. If future experiments, like next-generation cosmic microwave background telescopes, finally detect the clear, strong signal of primordial B-mode polarization, it would be a monumental triumph for inflation. But if they continue to see nothing, if the search for these primordial ripples keeps coming up empty, then the ekpyrotic model, with its prediction of a silent gravitational wave background, suddenly becomes a much more compelling candidate. It reframes the quiet we might hear not as a failure to detect, but as the signature of a universe born from a structured, cyclical collision rather than a chaotic, inflationary burst. This theory challenges not just how the universe began, but the very nature of time itself, proposing an eternal return where each Big Bang is not a unique beginning, but simply the latest chapter in an infinite cosmic story. This next theory invites us to ponder a possibility that redefines the very meaning of the beginning. What if the Big Bang was not a true origin point, but simply a turning point? This is the core of the pre-Big Bang scenario, a fascinating idea emerging from the depths of string theory that paints a picture of a universe with a past that stretches back far beyond the moment of its greatest density. To understand this, we need to let go of the idea of a singular starting gun. Instead, imagine our universe in a state of relentless, slow contraction. For an almost unimaginable duration, all the matter and energy that currently makes up our expanding cosmos was instead drawn closer and closer together. Space itself was shrinking. This wasn't a chaotic collapse into a point, but a gradual, steady squeeze. According to this model, as the universe contracted, the energy density and the curvature of spacetime would have increased, but they would have done so in a controlled, smooth manner, avoiding the infinitely dense singularity that traditional physics struggles to explain. Then, at a certain point, a moment of maximum compression, this contraction reached its limit. Rather than vanishing into a paradox, the universe rebounded. This big bounce initiated the phase we are in now, the great expansion that began with the hot, dense state we call the Big Bang. The gravitational waves generated in such a scenario would be profoundly different from those predicted by inflation. During the long, slow contraction phase, any pre-existing quantum fluctuations or ripples would have also been compressed. This process would have amplified their frequencies, effectively shifting them to much higher energies. Then, during the bounce and the subsequent expansion, these waves would be stretched back out. The resulting signal would be a complex spectrum of primordial gravitational waves, but one with a very specific and telling signature. Their intensity would not be uniform across all frequencies. Instead, the spectrum would tilt dramatically, with the waves being significantly stronger at much higher frequencies than those predicted by inflationary models. This prediction opens up an entirely new observational frontier. Our current detectors like LIGO and future space-based observatories like LISA are tuned to listen for gravitational waves within specific frequency bands. The pre-Big Bang scenario suggests that the most telling evidence of our cosmic origin might not be in those bands, but at frequencies far higher than anything we can currently detect. It implies that the universe's first whisper might be a shriek, a high-frequency signal waiting for a generation of technology advanced enough to hear it. Finding such a signal would be monumental. It wouldn't just tell us about the moment of the bounce, it would carry encoded information about the entire contracting phase that preceded it. These waves would be fossils from a time before our time, a direct messenger from the universe's previous incarnation, offering us a glimpse into an era that, according to standard cosmology, simply did not exist. This theory transforms the Big Bang from a creation event into a transformational one, suggesting our universe may have a history that extends back into an immeasurable past. Now we turn our gaze to the most fundamental scale of reality, a realm so tiny it challenges the very definitions of space and time. This is the domain of quantum gravity, and our seventh theory proposes that the universe's very first ripples were born not from cosmic events, but from the frothy, turbulent nature of spacetime itself at the moment of creation. To understand this, we have to venture down to the Planck scale, a size so infinitesimally small that our conventional physics, the reliable rules of Einstein's general relativity, simply breaks down. At a distance of 10 to the minus 35 meters, spacetime is no longer the smooth, continuous fabric we imagine. Instead, it's believed to become a seething, chaotic foam where tiny wormholes might spontaneously form and vanish, and where the concepts of here and there lose all meaning. In this quantum foam, gravity is no longer a gentle curve in spacetime. It becomes a wild, fluctuating quantum field, subject to the same strange probabilistic rules that govern particles. It is within this primordial chaos that the seeds of primordial gravitational waves could have been sown. The theory suggests that the violent, unpredictable fluctuations of spacetime at the Planck scale, amplified by the incredible energies of the Big Bang, were directly imprinted onto the universe. These wouldn't be the amplified quantum fluctuations from inflation. These would be the raw, unfiltered tremors of quantum gravity itself, frozen into the cosmos as it expanded and cooled. The resulting gravitational wave background would carry a unique fingerprint, a specific pattern across different frequencies that reflects the fundamental quantum nature of gravity. Detecting this pattern would be like finding the first recording of reality's most basic operating system, a direct signal from the fuzzy edge where physics as we know it begins and ends. This is profoundly important because quantum gravity remains the single greatest unsolved problem in fundamental physics. For decades, theorists have proposed elegant ideas: string theory, loop quantum gravity, causal dynamical triangulation, but a major hurdle has been a lack of experimental data. The energies required to probe the Planck scale are so astronomically high that building a particle accelerator capable of reaching them would need a machine larger than our solar system. We are, in a sense, trapped from directly testing these theories. This is where primordial gravitational waves offer a breathtaking way out. They originated at those very energies, at the very moment the universe was compact enough to experience these quantum gravitational effects. They have been traveling for 13.8 billion years, bringing us data from a regime we could never hope to recreate. The challenge, of course, is immense. The signals would be incredibly faint, buried under the combined gravitational wave noise from every black hole merger, neutron star collision, and other astrophysical event throughout cosmic history. Disentangling this specific quantum gravitational whisper from the cosmic roar will require detectors of unbelievable sensitivity, perhaps a future generation of observatories we can only dream of today. But if we succeed, the payoff would be nothing less than revolutionary. It would provide our first concrete evidence for a theory of quantum gravity, allowing us to finally move beyond speculation and understand how the universe truly works at its most fundamental level. The quiet hum of these waves could be the key that unlocks the final secrets of reality, revealing the quantum code from which spacetime itself is woven. While the previous theories have looked to cosmic events and the fabric of spacetime itself, our eighth theory introduces a new and deeply fascinating character to the story, a hypothetical particle that has captivated physicists for decades. This is the action, a particle first proposed not to explain the cosmos, but to solve a deeply perplexing mystery in the realm of the very small, known as the strong CP problem. In simple terms, the equations governing the strong nuclear force, the glue that holds atomic nuclei together, seem to allow for a certain kind of asymmetry that should affect neutrons. This asymmetry should cause a neutron in an electric field to behave like a tiny compass needle experiencing a torque. Yet, when measured, this effect is astonishingly absent. The neutron's electric dipole moment is zero to an incredible degree of precision, suggesting a symmetry in the laws of physics that is beautifully perfect, but for which we have no explanation. The action was proposed as an elegant solution, a new field that would effectively sweep this problem under the cosmic rug, restoring this natural symmetry. But the story of the action quickly expanded from a solution to a particle physics puzzle to a prime candidate for the universe's greatest mystery, dark matter. If actions were created in abundance in the early universe and are very light and slow-moving, they could naturally account for the invisible mass that shapes galaxies and binds clusters together. For this to work, however, we need a mechanism to produce them in vast quantities. This is where the early universe sets the stage. As the cosmos cooled, it's theorized that the field associated with actions may have undergone a phase transition. Imagine this field as a vast cosmic hillside covered in a uniform layer of fog. As the temperature drops, this fog becomes unstable and must condense, but it can't decide where to form the first droplet. At different points across the hillside, the field randomly chooses a value to settle into, like countless raindrops starting to form independently. This is where the phenomenon of cosmic strings reappears, but with a twist. In the action field, these aren't the infinitely massive filaments of energy we discussed earlier, but topological defects specific to this field. As these different regions where the action field has chosen a value grow and meet each other, they don't always match up perfectly. The misalignment between these domains can get tangled, forming networks of cosmic strings made purely from the action field itself. This network is not static, it's dynamic and unstable. The string loops oscillate violently, and most importantly, they can decay. And it's in this decay, the final, energetic dissolution of these actionic string loops, that they are predicted to radiate a significant portion of their energy not just in actions but in gravitational waves. The resulting signal would be a unique and persistent hum of gravitational radiation, a background created by the death throes of countless string loops throughout cosmic history. This background would have a very specific spectrum, a particular shape across different frequencies that would act like a fingerprint for the action. The frequency and intensity of these waves are directly tied to the mass of the action particle and the energy scale at which it was created. Therefore, detecting this specific gravitational wave signature wouldn't just be another astronomical discovery. It would be a direct confirmation of the action's existence and a measurement of its fundamental properties. It would kill two of the biggest mysteries in physics with one stone, simultaneously solving the strong CP problem and identifying the particle that makes up dark matter. We would finally know what the invisible backbone of our cosmos is truly made of, all by listening to the faint, ringing echo of its birth pangs. This turbulent finale of inflation, known as the reheating era, marks the moment the universe truly came alive. After its phenomenal exponential stretch, the field that drove inflation, often called the inflaton, began to lose its energy. But this energy didn't just vanish, it had to go somewhere. It cascaded into the universe in a spectacular decay, flooding the cosmos with the hot plasma of particles that would eventually form everything we see. But this transfer of energy wasn't a gentle trickle. It was a catastrophic, violent cascade, and it's in this chaos that our next source of primordial ripples is found. Think of the inflaton field as a massive ball perched at the top of a very steep hill. This position represents the high energy state that powered inflation. As the expansion slows, this ball begins to roll down the hill, picking up speed. But instead of rolling smoothly, it oscillates wildly, swinging back and forth around the bottom of the valley. Each one of these violent oscillations represents the inflaton field converting its pent-up energy into particles. In some models, this process is relatively smooth and efficient. In others, it's far more dramatic. The field doesn't just oscillate, it fragments. It can develop instabilities, breaking apart into smaller, localized clumps of energy that then decay independently, like a massive firework bursting into 1,000 smaller sparks, each igniting its own patch of the cosmos. This is where the turbulence comes in. The universe during this period wouldn't have been a uniform soup, it would have been a seething, chaotic cauldron. These different clumps of energy, decaying at slightly different rates and times, would have created intense variations in density and pressure. These variations would have spawned powerful shock waves, rippling through the nascent particle plasma. Furthermore, if the inflaton field was coupled to other matter fields, the process could have involved a phenomenon called parametric resonance. This is a bit like pushing a child on a swing at just the right time with each oscillation. A small amount of energy is added with each push, leading to an enormous amplified output. In the early universe, this resonance would have led to an explosive, non-linear production of particles, a burst of creation so violent and uneven that it would have shaken the very fabric of spacetime, generating a storm of gravitational waves. Each proposed mechanism for this reheating process leaves a distinct mark on these gravitational waves. A slow, smooth decay would produce a relatively weak and broad-spectrum signal. But a violent, resonant decay would generate a gravitational wave background that is much stronger and, crucially, peaked at a very specific frequency. This frequency is directly tied to the mass of the inflattened field and the temperature of the universe at the moment of reheating. It's a direct echo of the physics that ended inflation and began the hot Big Bang. By searching for this peaked signature across the gravitational wave spectrum, we are effectively trying to listen for the exact note the universe played when it switched from stretching to burning. Finding it would tell us not just that inflation happened, but precisely how it ended, giving us a direct window into the properties of the field that shaped our entire cosmic destiny. This brings us to a theory that is perhaps the most elegant and elusive in all of modern physics, an idea so powerful it could answer several of the universe's deepest questions at once. This is supersymmetry, often nicknamed SUSY, a concept that proposes a breathtaking and profound partnership at the heart of reality. It suggests that for every known particle in the Standard Model, every electron, every quark, every photon, there exists a hidden superpartner. An electron would be paired with a selectron, a quark with a squark, a photon with a photino. In this perfectly symmetric view of the cosmos, the fundamental divide between the particles that make up matter and the particles that carry forces would vanish. They would be two sides of the same exquisite coin. In the earliest, hottest moments of the universe, this symmetry would have been unbroken. Matter particles and force particles would have been indistinguishable, united in a state of perfect balance. But as the cosmos expanded and cooled, this perfect symmetry, like so many others before it, had to break. The superpartners, if they exist, would have acquired large masses, making them incredibly heavy and so far undetectable by our current particle colliders. This breaking of supersymmetry wasn't a quiet event. It was a phase transition, a seismic shift in the laws of physics that would have sent shockwaves through the very foundations of spacetime. The energy released as the universe settled into its new, asymmetric state would have been immense, and the process would have been highly turbulent. Just as the collision of bubbles in an earlier theory generated gravitational waves, the violent breaking of supersymmetry would have rippled the fabric of the cosmos, creating a unique background of primordial gravitational waves. The signal from this event would be a clear fingerprint carrying specific information about the energy scale at which supersymmetry broke. This is where the theory connects to one of particle physics' most vexing issues, the hierarchy problem. In simple terms, this is the question of why gravity is so unbelievably weaker than all the other forces. The electromagnetic force is 1,000 trillion times stronger than gravity. This makes no sense unless there is a hidden mechanism, a symmetry, that naturally cancels out the extreme values and brings balance to the equations. Supersymmetry is the leading candidate to provide that cancellation. The gravitational waves generated from its breaking would not just be a byproduct, they would be a direct measurement of the energy at which this cosmic correction occurred. By detecting the specific frequency and amplitude of these waves, we could effectively weigh the superpartners and confirm the solution to the hierarchy problem, all without ever directly smashing a single particle in a lab. This presents a thrilling possibility. Our largest particle accelerators, like the Large Hadron Collider, have been searching for evidence of these superpartners for years without success. It's possible they are simply too massive to be created at the energies we can currently achieve. but the early universe was the ultimate particle accelerator, operating at energies we can only dream of. The gravitational waves from supersymmetry breaking are a fossilized record of that incredible experiment. By building sensitive enough telescopes to listen for this specific hum, we could effectively peer into a realm of physics that is permanently beyond the reach of our earthly machines, finding evidence for a theory that would elegantly tie together the entire framework of modern physics and finally explain why the universe has the structure that it does. Beyond the singular threads of cosmic strings, the early universe may have woven a far more complex tapestry of flaws into its very fabric. This leads us to the cosmic defect network theory, which proposes that the chaotic process of cosmic phase transitions could have spawned an entire zoo of exotic structures known as topological defects. These aren't mistakes in the usual sense, but rather inevitable consequences, like cracks forming in ice as it freezes, when the universe's fundamental fields cooled and settled into their current state. The type of defect that forms depends entirely on the abstract, mathematical shape of the field's potential energy landscape, a topology that dictates what kind of imperfections can get trapped as reality changes phase. We've already met one member of this zoo, the one-dimensional cosmic string, but the family is much larger. Imagine a vast, three-dimensional field where every point in space must choose one of two possible values, like a cosmic coin toss deciding between heads or tails. As the universe cools, different regions make independent choices. Where domains of heads meet domains of tails, a two-dimensional sheet must form to separate them. This is a domain wall, an incredibly thin yet vast membrane of concentrated energy slicing through the cosmos. These walls would be truly formidable objects with surface densities so immense that even a patch the size of a football field could contain more mass than our entire galaxy. Their gravitational influence would be devastatingly disruptive, and their oscillations and interactions would be a tremendous source of gravitational waves. Then there is the most elusive defect of all, the magnetic monopole. In our everyday experience, magnets always have two poles, a north and a south. You can break a magnet in half, but you just get two smaller magnets, each with its own north and south pole. A true magnetic monopole would be a particle that is just a north pole, with no accompanying south or vice versa. Most grand unified theories predict that these exotic particles should have been created in copious amounts in the early universe. They would be point-like defects, incredibly massive and carrying a powerful magnetic charge. A network of these monopoles connected by cosmic strings could have formed a dynamic web, with the strings stretching and moving as the monopoles pulled on them, generating a persistent background of gravitational radiation through their complex motion. The gravitational wave signals from such a complex network would be a rich symphony compared to a single note. The slow, grand oscillations of vast domain walls would produce a low-frequency hum. The violent snaps and relativistic oscillations of cosmic strings would create sharper, more distinct bursts. The relentless motion of a monopole string network would contribute a continuous stochastic background. Each type of defect imprints its own unique signature onto the spectrum of gravitational waves, a specific pattern of intensity across different frequencies. Detecting this combined signal and untangling its components would be like an archaeologist not just finding one ancient tool, but uncovering an entire workshop, giving us a complete picture of the types of phase transitions that occurred and the specific symmetries that were broken in the first moments of time. It would reveal the deepest architectural blueprints of reality, showing us the cracks that formed as the universe's fundamental laws cooled into their current familiar form. But to truly grasp the potential of these waves to rewrite our most fundamental laws, we must venture into a realm where Einstein's theory of gravity, the very foundation of modern cosmology, might not be the final word. This is the world of modified gravity, a landscape of theories that propose our understanding of gravity, while incredibly successful, might be incomplete on the largest cosmic scales or the very smallest. These aren't wild speculations, they are rigorous mathematical frameworks designed to solve some of the most perplexing problems in physics, like the nature of dark energy or the mystery of dark matter. And crucially, each one of these alternative theories makes a distinct prediction about the character of the universe's first gravitational ripples. Consider the cornerstone of Einstein's general relativity, the graviton, the hypothetical particle that mediates the force of gravity. In its purest form, this particle is massless, which is why gravity has an infinite range, and it has two possible polarization states essentially, two ways it can wiggle as it travels through spacetime. This results in a very specific, clean signature for the gravitational waves it produces. But what if the graviton isn't massless? This is the premise of massive gravity theories, which propose that the graviton has a tiny but non-zero mass. This single change has profound implications. A massive graviton would travel slightly slower than the speed of light, and it would have additional polarization states, not just two, but potentially 5 unique ways to vibrate. This would dramatically alter the pattern of the primordial gravitational wave background. The signal wouldn't be as clean, it would be richer, more complex, and would carry an imprint of that mass across different frequencies. Detecting these extra polarization states would be a direct indicator that we need to add a new term to Einstein's equations. Then there are even broader frameworks like Horn-Desky theories, which represent the most general possible theories of gravity that can be described by a single extra field and still adhere to the sacred principles of physics like Lorentz invariance. These theories can produce truly exotic effects. In some models, the speed of gravitational waves can differ from the speed of light, a possibility that was shockingly ruled out by the nearly simultaneous detection of light and gravitational waves from a neutron-star merger in 2017, constraining many such ideas. But other Horn-Desky predictions remain viable. For instance, gravity could leak into extra dimensions over large distances, or the fundamental constants of nature, like the strength of gravity, might have been different in the past. Each of these scenarios would leave a distinct scar on the primordial gravitational wave spectrum, affecting its amplitude and its slope across different frequencies. This is why the search for these waves is so much more than a hunt for confirmation of inflation. It is a direct test of gravity itself. The primordial gravitational wave background is a fossilized record from a time when the universe was so energetic that any subtle differences between these theories would have been magnified. General relativity predicts one very specific pattern for this fossil. Every modified gravity theory predicts a different one. By building sensitive enough detectors to measure not just the presence of these waves, but their precise properties, their polarization, their spectrum, their amplitude, we are effectively conducting an experiment on the laws of physics as they were at the highest energies imaginable. A clear detection that matches Einstein's prediction would be a monumental triumph for general relativity, proving its dominance even at the very beginning of time. But a detection that shows a different pattern would be arguably even more revolutionary, forcing us to rewrite the textbooks and finally understand gravity not as Einstein saw it, but as the universe truly intends it to be. But what if the key to unlocking the universe's first whispers isn't found in the fiery processes of creation, but in the nature of its most mysterious and abundant component? This brings us to a compelling and deeply interconnected theory, the idea that dark matter itself could have been the architect of some of the primordial gravitational waves we are trying to detect. We know dark matter exists. Its gravitational pull dictates the motion of galaxies and shapes the cosmos on the largest scales. Yet, for all its influence, it remains completely invisible, refusing to interact with light or ordinary matter in any way other than through gravity. This profound mystery means that the birth of dark matter in the early universe is a story written in a language we are only beginning to understand, the language of gravitational waves. To explore this, we need to consider the leading candidates for what dark matter actually is. One of the most prominent ideas is that it consists of weakly interacting massive particles, or WIMP. These are hypothetical particles that are thought to be their own antiparticles. In the seething heat of the early universe, WIMP would have been created and annihilated in a constant, frenetic dance. As the cosmos expanded and cooled, however, the density would have dropped to a point where these particles could no longer find each other to annihilate, freezing out and leaving behind a stable relic population that becomes the dark matter we infer today. This process of thermal freeze-out is a cornerstone of modern cosmology, but in some models this freeze-out isn't perfectly smooth. It could occur through a first-order phase transition, a dramatic shift where bubbles of the new phase of the universe nucleate and expand. The collisions of these bubble walls would be incredibly violent events, shaking space-time and generating a potent background of gravitational waves with a very specific frequency signature tied to the energy scale of the WIMP mass. Another fascinating dark matter candidate is the sterile neutrino. Unlike the standard neutrinos we know, which interact via the weak nuclear force, a sterile neutrino would, as its name implies, interact only through gravity, making it an ideal dark matter particle. One proposed mechanism for their creation is through the oscillations of ordinary neutrinos into sterile ones in the early universe. If this process occurred resonantly, it could have generated significant lepton number asymmetries, imbalances in the number of particles versus antiparticles. These asymmetries can drive powerful instabilities in the primordial plasma, large-scale convulsions that could have rippled the fabric of spacetime. The gravitational waves from such an event would carry a unique fingerprint, a direct signal from the moment a portion of the universe's matter decided to become almost entirely invisible. Perhaps the most dramatic dark matter scenario involves a dark sector, a whole separate set of particles and forces that interact with our familiar world only through gravity. This hidden realm could have its own rich physics, including a dark force mediated by a dark photon. In such a model, dark matter particles could attract each other through this dark force, forming dense clumps that eventually collapse into primordial black holes. The actual collapse of these dark matter clumps or their subsequent mergers would be a tremendous source of gravitational waves. Furthermore, if this dark sector experienced its own phase transitions, separate from the visible universe, the resulting bubble collisions and turbulence would generate a gravitational wave background all their own, a parallel cosmic narrative happening in a hidden dimension of reality, its echoes faintly crossing over into our own. The incredible promise of this theory is that it turns the hunt for primordial gravitational waves into a dual discovery mission. Detecting a specific, unexpected signal in the gravitational wave background could do more than just confirm a process in the early universe. It could finally reveal the identity of dark matter itself. The frequency and amplitude of the waves act as a cosmic barcode, scanning the energy scale and the physics of the process that created them. A detection linked to a WIMP freeze-out would tell us the particle's mass. A signal from a dark sector phase transition would reveal the temperature of that hidden world. After decades of searching for dark matter directly in deep underground labs or indirectly with space telescopes, we might finally hear its birth cry through the subtle vibrations it imprinted on spacetime at the dawn of time, a vibration that has been traveling through the expanding cosmos for billions of years, waiting for us to develop the technology to listen. Imagine the universe cooling from its initial, unimaginably hot state, not like water smoothly turning to ice, but like a supercooled liquid holding its form until a sudden, violent snap. This is the essence of a first-order phase transition, a dramatic and explosive shift in the state of the cosmos that could have generated some of the most powerful primordial gravitational waves of all. While many phase changes happen smoothly, a first-order transition is different. It requires an activation energy, a push to get over a hump, meaning the universe can exist in a supercooled, metastable state like water, remaining liquid well below 0 degrees Celsius until the smallest fluctuation triggers a catastrophic and rapid change. In this supercooled state, the transition doesn't happen everywhere at once. Instead, it begins at random points where tiny quantum fluctuations provide that necessary spark. At these points, bubbles of the new, true vacuum phase of the universe suddenly nucleate. Picture these not as soap bubbles, but as spheres of a new reality, where the laws of physics have fundamentally shifted to a lower energy state. These bubbles are born and then expand at velocities approaching the speed of light, their walls containing an immense concentration of energy. As they grow, they push against the surrounding sea of the old, high-energy phase, and the universe becomes a chaotic froth of these colliding domains. The gravitational waves are generated in two spectacular ways from this frenzy. The first and most intuitive source is the direct collision of these incredibly energetic bubble walls. When two such walls smash into each other, the event is cataclysmic, a monumental release of energy that sends a powerful, sharp ripple through the fabric of spacetime itself. But there's a second, potentially even more productive source: sound waves. Think of the bubble not just as a wall, but as a piston. As it expands at near light speed into the primordial plasma, the thick soup of particles that filled the early universe, it acts like a cosmic piston driving a shockwave through this medium. These are not gentle sound waves, they are violent, thunderous vibrations that shake the entire cosmos. The resulting turbulence in the plasma is immense, and this churning motion of vast amounts of mass and energy is a tremendously efficient generator of gravitational waves. The resulting signal would be a rich background hum, but one with a very distinct character. Its spectrum, its intensity across different frequencies, would carry a clear fingerprint of the physics that drove it. The frequency of the waves would tell us the temperature of the universe at the moment of the transition, which in turn points to the energy scale of the new physics involved. The amplitude or strength of the signal would reveal how violent the process was. A longer period of supercooling would build up more latent energy, leading to more powerful bubble collisions and louder gravitational waves. This makes the search for this signal a direct probe into the fundamental forces at work when the universe was just a fraction of a second old. Detecting it would be like hearing the thunder from the universe's most dramatic storm, a permanent echo of the moment reality literally snapped into a new form. Now we stretch our imagination beyond the three dimensions we know and love, venturing into a realm that sounds like pure science fiction but is a serious frontier of theoretical physics. This is the theory of extra dimensions, a concept that suggests the fabric of our reality is woven with more spatial dimensions than just length, width, and height. These hidden dimensions, if they exist, would be curled up or warped in ways that make them imperceptible to us in our everyday lives. Much like a garden hose looks like a one-dimensional line from a distance, but up close reveals a two-dimensional surface curled into a cylinder. According to string theory, the leading framework that requires these extra dimensions for its mathematical consistency, the universe might actually have 10 or even 11 dimensions in total. The implications of this for the birth of our cosmos, and specifically for the first gravitational ripples, are nothing short of revolutionary. During the universe's very first instance, all of these dimensions, including the extra ones, would have been unfurled and operating on an equal footing, existing at a scale so tiny we can scarcely conceive of it. As the cosmos expanded and cooled from the Big Bang, something profound is theorized to have happened. The three spatial dimensions we're familiar with expanded exponentially to become the vast cosmic stage we see today. But the extra dimensions, they failed to inflate. Instead, they remained compactified, curled up into a space so infinitesimally small that they are effectively hidden from view. This process of dimensional compaction wasn't necessarily a quiet one. The dynamic act of these dimensions stabilizing and curling up would have released an enormous amount of energy, shaking the very foundation of space-time and generating powerful gravitational waves in the process. But the influence of extra dimensions wouldn't stop there. Gravitational waves are at their core vibrations in the geometry of space-time. In a universe with more than 3 spatial dimensions, these waves wouldn't be confined to just our familiar 3-dimensional brane of existence. They could propagate into the bulk, the higher dimensional space that contains our reality. This leakage would fundamentally alter the properties of the gravitational waves we could potentially detect. For one, their strength would be diluted. Some of the energy of the wave would effectively vanish into these hidden dimensions, meaning the primordial gravitational wave background we might measure could be significantly weaker than predictions from standard 4-dimensional physics would suggest. This could explain why we haven't detected it yet. Even more tantalizing is the effect on the wave spectrum. The way gravity behaves across different scales changes in models with extra dimensions. This would imprint a specific, recognizable distortion onto the spectrum of primordial gravitational waves, a kind of kink or change in slope at certain frequencies. Detecting this precise distortion would be a smoking gun, the first direct experimental evidence not just for extra dimensions, but for the entire edifice of string theory itself. We would finally have a window into the complete geometry of reality, proving that the universe is indeed built upon a deeper, more complex spatial architecture than we ever dreamed possible. It would transform our understanding from a universe of 3 dimensions to a multiverse of higher dimensional spaces, with our own world just one visible slice of a much grander cosmic whole. This idea takes us into the profound and often counterintuitive relationship between gravity and one of the universe's most subtle properties, handedness, or what physicists call parity. In our everyday experience, the laws of physics seem perfectly symmetrical. A physical process and its mirror image should, in principle, follow the same rules. This is known as parity symmetry, but in the 1950s, to the astonishment of the physics community, this was discovered not to be universally true. In the realm of the weak nuclear force, the mirror image of a process like beta decay is forbidden. The universe at a fundamental level can tell its left from its right. This discovery of parity violation was a monumental shock, revealing a deep-seated asymmetry woven into the fabric of reality. Chern-Simons gravity is a theoretical extension of Einstein's general relativity that asks a daring question. What if gravity also violates parity? What if the force that shapes the cosmos itself has a preferred handedness? The theory introduces a new field, often related to the elusive action we discussed earlier, that couples directly to the curvature of spacetime. This coupling acts like a cosmic filter, making spacetime react differently to ripples that are left-handed versus those that are right-handed. In standard general relativity, a gravitational wave is an oscillation that can be thought of as spinning in one of 2 possible ways as it travels through space, like a corkscrew rotating clockwise or counterclockwise. These 2 states are perfectly symmetric and equivalent, but in Chern-Simons gravity, one of these rotations is favored over the other. The theory effectively makes spacetime birefringent for gravity, much like certain crystals are birefringent for light, splitting a beam into 2 components with different polarizations. This leads to a spectacular and unique prediction for primordial gravitational waves. Instead of the 2 standard, symmetric polarization modes, the waves produced in the early universe under Chern-Simons gravity would have an overwhelming imbalance. One-handedness would be dramatically amplified while the other would be suppressed. The resulting gravitational wave background would not be an even hum. It would be a polarized chorus, a clear and overwhelming preference for one type of spin over the other imprinted onto the oldest vibrations in the cosmos. Detecting this distinct, circularly polarized signal would be a smoking gun, irrefutable evidence that gravity is not the perfectly symmetric force Einstein described, but one that participates in the universe's inherent chirality. The implications of such a discovery would be earth-shattering, reaching far beyond just rewriting a textbook equation. It would force us to confront a cosmos that is fundamentally lopsided at the most profound level, from the decay of a neutron to the collapse of a star to the very expansion of the universe itself. This gravitational parity violation could provide a natural mechanism for explaining the overwhelming matter-antimatter asymmetry we see in the universe while we are surrounded by matter with almost no antimatter to be found. It could be the key that unlocks the door to a truly unified theory, one that seamlessly incorporates gravity with the other fundamental forces by revealing this shared asymmetric character. Finding the polarized echo of Chern-Simons gravity would be more than just detecting a wave. It would be reading the universe's preference for left or right, revealing a fundamental bias in nature that has shaped everything from the first instance of time to our very existence. And yet, even the most violent bubble collisions might pale in comparison to the raw, untamed chaos of the universe's very first moments. This brings us to a theory that dives into the heart of the inflationary finale, a period of unimaginable turbulence known as preheating. Think of it as the universe's most spectacular wake-up call. After inflation's incredible exponential stretch, the field that powered it, the inflaton, was left holding a colossal amount of pent-up energy. This energy had to be transferred, and quickly, to fill the universe with the hot plasma of particles that would become the raw material for everything. But this transfer wasn't a calm, orderly handoff. It was a catastrophic, resonant cascade, a feedback loop of explosive particle production that shook the very foundations of reality and sent gravitational ripples echoing across the newborn cosmos. The process begins as the inflaton field, having driven the expansion, starts to oscillate around the bottom of its energy potential. Imagine a giant bell that has just been struck, ringing with an incredibly powerful and pure tone. Now, if that bell is coupled to other fields, the fields that represent all the known particles of the Standard Model, its powerful oscillations can drive those other fields to vibrate in resonance. This is the phenomenon of parametric resonance. It's like pushing a child on a swing. If you push at just the right moment in the swing's arc, a very small push can produce a huge, amplified output. In the early universe, the inflaton's oscillations provided that perfectly timed push, but on a cosmic scale. Certain modes or frequencies of the particle fields received a tremendous amount of energy, growing exponentially in a runaway explosion of particle production. The universe didn't just warm up, it underwent a violent, non-linear burst of creation, transforming the cold, empty expanse left by inflation into a seething, superheated plasma in a fraction of a second. This period was far from uniform. It was a scene of extreme instability and chaos. In different regions of space, different modes of the particle fields were amplified, creating gigantic, explosive inhomogeneities. Vast waves of concentrated energy, known as tachyonic instabilities, raced through the cosmos. These weren't gentle ripples, they were violent, large amplitude fluctuations in the density of the newly created particles. The universe became a turbulent, churning cauldron, with shockwaves propagating through the dense plasma. It is this large-scale, violent motion of enormous amounts of mass energy that acts as a tremendously efficient generator of gravitational waves. The sheer scale of the turbulence, with irregularities spanning large portions of the observable universe, means the gravitational waves produced would be long wavelength and incredibly powerful, creating a distinct background hum that permeates all of space. The specific signature of these waves depends heavily on the model of preheating. In some scenarios, the process is brief and incredibly efficient, leading to a gravitational wave spectrum with a sharp, narrow peak at a specific frequency. This frequency is a direct messenger telling us the mass of the inflaton field and the temperature of the universe at the moment of this explosive transition. Other models, where preheating is less efficient and the instabilities grow more slowly, produce a broader spectrum of gravitational radiation, The amplitude or loudness of the signal is a direct measure of how violent the process was. By searching for this specific peak or shape in the gravitational wave background, we are effectively tuning into the frequency of the universe's first great explosion of life, listening for the exact note it played as it switched from the silent stretch of inflation to the roaring fire of the hot Big Bang. Detecting it would give us a direct window into the physics of the inflaton's decay, revealing not just that inflation happened, but precisely how it ended and brought the universe to life. While we often picture the birth of gravitational waves in the cold, abstract realm of quantum fluctuations or the violent crashes of cosmic defects, there's another, more thermodynamic source of these ripples that emerged from the sheer, raw heat of the young cosmos. This theory proposes that the universe's first ripples weren't just quantum mechanical or cosmological in origin, they were, in a very real sense, thermal. To grasp this, we need to step away from the vacuum of empty space and into the dense, chaotic plasma that filled the universe in its first few moments. This wasn't a quiet, empty place. It was a seething, roaring ocean of energy, a primordial soup of particles and radiation at temperatures so high that matter and light were locked in a constant, frenetic dance. Within this plasma, energy was never perfectly distributed. Even in a state of thermal equilibrium, there are constant, tiny fluctuations in density and pressure. Particles jostle and collide, creating minute, temporary hotspots and cold spots. These are thermal fluctuations, the atomic scale vibrations of a tremendously hot gas. In our everyday world, these fluctuations are far too small to have any gravitational consequence, but in the early universe, the scale was unimaginably different. The entire cosmos was smaller than a grapefruit and hotter than the core of a star. In that environment, these thermal fluctuations were not tiny. They were colossal, encompassing vast regions of space. And according to general relativity, any distribution of energy and pressure that isn't perfectly smooth will generate gravitational waves. The chaotic churning of this ultra-hot plasma, with its massive density waves and pressure oscillations, would have constantly shaken the fabric of spacetime, producing a background hum of gravitational radiation. The resulting signal would have a very special character. A perfect blackbody, like the interior of a hot oven, emits radiation across a smooth spectrum of frequencies with a peak that depends solely on its temperature. The cosmic microwave background is the most famous blackbody spectrum in the universe. This thermal gravitational wave theory suggests that these primordial waves could also have a blackbody-like spectrum. Their intensity across different frequencies wouldn't be flat or peaked from a specific event. It would instead carry the clean, thermodynamic fingerprint of the temperature of the universe at the moment they were generated. The frequency of the peak would tell us directly how hot the cosmos was, acting as a cosmic thermometer for a time long before the first atoms ever formed. This presents a fascinating contrast to the more popular quantum generation mechanisms. Quantum fluctuations from inflation are stretched from the microscopic to the cosmic scale, creating a spectrum that is nearly scale invariant. Its strength is roughly the same across a huge range of frequencies. Thermal gravitational waves, born from the macroscopic motion of a hot plasma, would have a very different spectral shape. They would be most powerful at frequencies corresponding to the typical size of the largest possible fluctuations in that plasma at that temperature, falling off sharply at both higher and lower frequencies. This creates a clear observational test. If we one day map the precise spectrum of the primordial gravitational wave background and find it matches a blackbody curve tied to a specific, incredibly high temperature, it would be powerful evidence that thermal processes played a dominant role. If the spectrum is flat, it points squarely to a quantum origin like inflation. We would be learning about the universe's earliest moments not by listening to the quiet whispers of the quantum vacuum, but by feeling the residual heat from its most fiery, turbulent youth. Now, let's shift our focus to a force that shapes galaxies and guides compass needles, a phenomenon so familiar we often take it for granted, and ask a profound question. Could the universe's magnetic personality have played a role in its very first vibrations? This is the magnetic field origin theory, a compelling idea that suggests the seeds of the cosmos's gravitational waves weren't sown in quantum foam or colliding brains, but in the turbulent, electrified dynamo of its own nascent magnetic fields. We see magnetic fields everywhere in the modern universe, wrapped around planets, threading through stars, and woven across entire galaxies. But where did these vast cosmic magnets come from? Their origin is one of astronomy's great unsolved puzzles. Some theories propose they were born primordially, generated in the extreme conditions of the very early universe, and if that's true, their formation would have been anything but quiet. To understand how a magnetic field can create a gravitational wave, we need to revisit a cornerstone of Einstein's theory. Anything that possesses energy and momentum can curve spacetime and generate gravity. A magnetic field, though invisible, is packed with energy. It exerts pressure and creates tension, and when such a field is in motion, its energy density fluctuates. Now picture the infant universe, a thick, hot plasma of charged particles, protons, electrons, and ions, all zipping around at near light speed. In this seething chaos, any tiny electric current could be amplified into a coherent magnetic field through processes like dynamo action, where the motion of the conductive plasma stretches and twists magnetic field lines, making them stronger. But the birth of these first large-scale magnetic fields would have been a violently turbulent event. The field lines wouldn't have lain down neatly. They would have been tangled, knotted, and whipped into a frenzy by the motions of the plasma, creating regions of immense magnetic stress. It is this turbulence, the chaotic, writhing motion of these powerful magnetic fields within the dense primordial soup, that could have shaken spacetime itself. As the field lines twisted and recoiled, their changing stress energy would have acted like a paddle stirring a pond, sending ripples out through the very fabric of the cosmos. These wouldn't be the clean, oscillatory waves from a black hole merger. They would be a stochastic background, a complex hum born from the combined roar of countless magnetic storms raging across the entire universe. The resulting gravitational wave signal would carry a unique signature, a spectrum of frequencies directly tied to the strength of those initial fields and the scale of the turbulence. Detecting this specific hum would be like finding the fossilized imprint of the universe's first great magnetic storms, a permanent record of the moment the cosmos became magnetized. This theory beautifully connects two seemingly disparate branches of astronomy: gravitational wave science and cosmic magnetism. A confirmed detection would not only reveal a new mechanism for generating primordial ripples, but would also solve the long-standing mystery of where magnetic fields come from, proving they are a fundamental and ancient feature of the cosmos, present almost from the very beginning. It suggests that the forces that create the aurora in our sky and shape the spiral arms of galaxies also played a part in ringing the universe like a bell, leaving a gravitational echo that has lasted for billions of years. Yet for all the violence of its birth, the universe harbors an even deeper mystery, one written not in the things we see, but in the things we don't. We are surrounded by a cosmos made almost entirely of matter. The stars, the planets, you and I, we are all built from protons, neutrons, and electrons. But the laws of physics, as far as we can tell, treat matter and antimatter with a stunning equality. For every particle created in the Big Bang, an antiparticle should have been created alongside it. And when matter and antimatter meet, they annihilate in a flash of pure energy. So the greatest puzzle of all is this: if the universe began with a perfect balance, why did that balance break? Why did a tiny 1 in a billion asymmetry favor matter, allowing a residue to survive that annihilation to form everything we know, instead of the entire cosmos simply vanishing into a featureless bath of radiation? This process, the genesis of that imbalance, is called baryogenesis, and it may have left behind a ringing testament to its occurrence in the form of gravitational waves. To understand how creating matter could also create ripples in spacetime, we need to look at the leading theories for how baryogenesis might have occurred. One of the most compelling mechanisms is called electroweak baryogenesis. This theory places the pivotal moment at the electroweak phase transition, when the electromagnetic and weak nuclear forces split from their unified state. In the standard picture, this transition is a smooth crossover, like butter slowly melting in a pan. But for electroweak baryogenesis to work, it needs to have been a first-order phase transition, a violent, sudden change, more like water explosively flashing into steam. In this scenario, bubbles of the new phase, where the forces have separated, would have nucleated and expanded at nearly the speed of light. Now, here's the crucial part. The walls of these expanding bubbles would have acted as powerful factories for creating matter. The physics is complex, but the essence is that the passing bubble wall would have interacted with particles in a way that treated matter and antimatter differently, a process that violates what's known as CP symmetry. This is the cosmic equivalent of a sieve that lets more sand pass through than gravel. As the bubble wall sweeps through space, it leaves in its wake a tiny excess of matter over antimatter. But the story doesn't end there. The expanding bubbles eventually collide, and when they do, the release of energy is cataclysmic. These violent collisions of bubble walls, along with the tremendous turbulence they generate in the primordial plasma, are a phenomenal source of gravitational waves. The resulting signal would be a powerful background hum, with a peak frequency that directly tells us the temperature of the universe at that critical moment, the energy scale of the electroweak transition, which we can calculate in our particle physics models. Detecting this specific gravitational wave signature would therefore be a double discovery. It would confirm the mechanism that created all the matter in the universe and provide direct evidence for physics beyond the standard model that allowed it to happen. Another elegant mechanism for creating the matter asymmetry is leptogenesis. This theory suggests that the imbalance didn't start with quarks and protons, but with the much lighter, ghostly particles called neutrinos. It proposes that incredibly heavy, right-handed neutrinos, partners to the ones we know, were created in the hot early universe. These particles are expected to be highly unstable, and as they decayed, they did so in a way that again violated CP symmetry. For every decay that produced a few more ordinary particles than antiparticles, another decay would have produced a few more antiparticles, but the net result was a slight overall lepton number asymmetry, an imbalance in the number of leptons, the family that includes electrons and neutrinos. Through a subtle and beautiful process involving the weak nuclear force, this lepton asymmetry was then converted into a baryon asymmetry, giving us the world of matter we see today. While the leptogenesis process itself might not be as directly violent as bubble collisions, it can still be intimately linked to gravitational wave production. Those heavy right-handed neutrinos are often theorized to acquire their mass through a phase transition associated with a new, grander symmetry in particle physics. This phase transition would itself be first order, proceeding through the same mechanism of bubble nucleation and collision. The gravitational waves from that transition would be the detectable signature. The frequency of these waves would be different from the electroweak signal. It would point to a much higher energy scale, telling us the mass of those heavy neutrinos and confirming that leptogenesis was the correct path nature took to fill the cosmos with stuff. In this way, the faintest vibrations in spacetime could reveal the origin of everything substantial, connecting the largest scales of the cosmos to the smallest scales of particle masses. The profound connection here is that the very same conditions needed to solve the matter-antimatter puzzle, a strong first-order, phase transition, and new physics that violates fundamental symmetries, are also prime generators of a loud, clear gravitational wave signal. The universe's gravitational wave background therefore becomes more than just a record of its expansion. It becomes a ledger of its contents, a permanent archive documenting how it managed to create something from what should have been nothing. Finding the specific fingerprint of baryogenesis in that background would answer one of the most fundamental questions we can ask: why are we here at all? It would transform our understanding from a universe of accidental residue to one with a defined physical process that ensured its own survival and complexity, a process whose echo we might one day hear ringing quietly through the void. But to truly bend our minds around the nature of reality at its most fundamental level, we must consider a possibility that redefines our very notion of a smooth, continuous cosmos. This is the theory of non-commutative geometry, a profound idea emerging from the quest to unify general relativity with quantum mechanics. It proposes that at the tiniest conceivable scales, near the Planck length, spacetime itself might not be the smooth, infinitely divisible backdrop we imagine. Instead, the familiar coordinates of space and time may cease to be simple numbers you can plug into an equation. They might become more like the operators we find in quantum mechanics, where the very act of measurement affects the outcome. In this bizarre and wonderful view, the fabric of the universe possesses a fundamental graininess, a pixelated structure where the order in which you measure things actually matters. The mathematical heart of this idea lies in the concept of non-commutativity. In our everyday world, numbers are commutative. 5 times 3 is the same as 3 times 5. The order of operation doesn't change the result, but in the quantum world, this isn't always true. For a particle, measuring its position first and its momentum second can give you a different overall result than if you measured its momentum first and its position second. Non-commutative geometry applies this same quantum principle to the coordinates of spacetime itself. It suggests that at the Planck scale, the measurement of one coordinate, say the x position of an event, interferes with the measurement of another, like its y position. The coordinates no longer commute. X times y is not equal to y times x. This introduces a fundamental limit to the precision with which we can ever know the location of an event in spacetime, a kind of universal blurriness woven into the fabric of reality. The universe, in essence, has a minimum resolution. This radical rethinking of spacetime's nature has dramatic implications for the universe's very first vibrations. In standard inflationary cosmology, the quantum fluctuations that get stretched into gravitational waves originate in a smooth, classical spacetime background. But if spacetime is inherently non-commutative at high energies, that background is fundamentally altered. The violent quantum jitters that serve as the seeds for these waves would be happening on a stage that is itself fuzzy and uncertain. This fuzziness acts as a kind of regulator, suppressing the generation of the very highest frequency gravitational waves. The non-commutative geometry effectively imposes a short-distance cutoff, preventing fluctuations of arbitrarily small wavelength from ever forming. It's as if the universe's pixelated nature puts a limit on how finely detailed its primordial ripples can be. The resulting gravitational wave background would carry a clear, testable signature of this underlying graininess. Instead of the nearly scale invariant spectrum predicted by standard inflation where the strength of the waves is roughly equal across all frequencies, the non-commutative model predicts a distinct deviation. The spectrum would be strongly suppressed at very high frequencies, those corresponding to wavelengths approaching the fundamental Planck scale. At lower frequencies, the spectrum would match the standard prediction, but this sharp cut-off at the high-frequency end would be a smoking gun. It would be a direct imprint of the universe's pixelated structure, a permanent record in the gravitational wave background that we are not living in a smooth, continuous cosmos, but one with a fundamental and indivisible resolution. Detecting this specific spectral distortion would be one of the most profound discoveries in all of physics, offering our first direct experimental window into the quantum nature of spacetime and gravity. revealing that the stage upon which the cosmic drama plays out is built from something far stranger and more wonderful than we ever conceived. This next theory invites us to question the very nature of our reality, proposing that the three-dimensional universe we experience might be nothing more than an incredibly detailed illusion, a cosmic projection playing out on a distant two-dimensional surface. This is the holographic principle, an idea that emerges from the study of black holes and our attempts to reconcile gravity with quantum mechanics. It suggests that all the information needed to describe everything within a volume of space, every star, every planet, every one of us, is actually encoded on its two-dimensional boundary like a fantastically complex piece of holographic film. The world we see and feel would be a three-dimensional projection of that data, a reality that is deep and rich but ultimately no more real than the image on a movie screen. This isn't just a philosophical thought experiment. It's a serious framework with profound implications for how we understand the birth of the cosmos and the gravitational waves it first produced. To grasp how this could affect the universe's earliest ripples, we need to consider the principle's origins in black hole physics. When an object falls into a black hole, it seems to vanish, which violates a fundamental quantum rule: information cannot be destroyed. The holographic principle solves this paradox by suggesting the information about that object isn't lost inside the hole. It's perfectly encoded on the black hole's event horizon, its two-dimensional surface. The entire interior is described by the physics on that boundary. Now, apply this mind-bending concept to the entire universe. The Big Bang can be thought of as the moment when our cosmic horizon was created. According to the holographic principle, the information for everything that would ever happen within our universe was imprinted on that lower dimensional boundary at the beginning of time. The subsequent expansion and evolution of the cosmos is just that data being read out and projected. This radical reconception of reality would inevitably leave its mark on the primordial gravitational wave background. In the standard inflationary picture, these waves are generated by quantum fluctuations within the three-dimensional volume of the young universe. But if the holographic principle is correct, those fluctuations weren't truly three-dimensional events. They were themselves projections of quantum information processing happening on the two-dimensional boundary. This difference in origin would subtly alter the statistical properties of the waves. The holographic framework imposes a fundamental limit on the number of degrees of freedom, the amount of information that can exist within a given volume. This limit could lead to a specific, predictable deviation in the gravitational wave spectrum, a slight but telling suppression of the very highest frequency waves. It's as if the pixelated resolution of our holographic universe puts a cap on how finely detailed those initial ripples can be. Detecting this specific signature would be one of the most revolutionary discoveries in science. It would provide the first hard, observational evidence that our perception of a three-dimensional world is an emergent illusion, a shadow cast by a more fundamental, lower-dimensional reality. The pattern of the primordial gravitational waves would act as a direct messenger from that boundary, confirming that the universe operates not like a vast, empty container, but like an incredibly complex and dynamic code. It would offer a breathtakingly elegant path toward a theory of quantum gravity, suggesting that gravity itself isn't a fundamental force in three dimensions, but an emergent phenomenon that arises from the quantum entanglement of information on the cosmic horizon. By listening to the faint hum of these ancient waves, we might finally crack the cosmic code and understand that we are not just living in the universe, but that we are a projection of its underlying holographic data. But to truly challenge our understanding of the cosmos's most fundamental constant, we must venture into a theory that questions the very backbone of modern physics, the unwavering speed of light. This is the variable speed of light theory, a proposition that in the extreme conditions of the universe's first instance, the speed of light might not have been the constant c we know today, but a value that changed over time. This isn't a minor adjustment, it's a potential revolution that would require us to rewrite Einstein's theory of relativity itself, and its implications for the universe's first gravitational ripples are profound and deeply telling. At the heart of Einstein's relativity is the idea that the speed of light in a vacuum is a universal constant, a cosmic speed limit that is the same for all observers regardless of their motion. This constancy is the foundation upon which all of modern cosmology is built, from the stretching of spacetime to the nature of black holes. But some physicists have asked a daring question. What if this constancy is only true for the mature, cooled-down universe we live in now? What if, in the unimaginable heat and density of the Big Bang, the rules were different? In this speculative view, the speed of light could have been vastly higher, a possibility that offers an elegant alternative to cosmic inflation for solving puzzles like the horizon problem. The mystery of why the universe appears so uniform in all directions. A faster speed of light in the past would have allowed distant regions to communicate and smooth out their differences long before the universe had a chance to become uneven. This radical shift would have dramatically altered the very genesis of gravitational waves. These ripples travel at the speed of light. It's woven into their fundamental nature. If the speed of light was variable, then so too was the speed of gravity. In the early moments of a high-speed light universe, gravitational waves would have propagated much faster, and their generation would have been governed by different physical laws. The processes we've discussed, inflation, phase transitions, quantum fluctuations, all depend critically on the fixed value of c to determine their scale and evolution. Change that constant and you change the entire script. The amplitude and frequency of the primordial gravitational wave background would be calculated differently, leading to a distinct predicted signal. A variable speed of light could, for instance, suppress the production of the longest wavelength gravitational waves or amplify certain frequency bands, creating a unique distortion in the spectrum that standard cosmology cannot explain. The most compelling aspect of this theory is that it offers a clear observational test. The propagation of gravitational waves is intimately tied to the expansion history of the universe. A changing speed of light would leave an imprint on how those waves are stretched as they travel across billions of light years. Future observatories, by measuring the gravitational wave background across a wide range of frequencies, could detect the telltale signs of this altered history. Finding a spectrum that deviates from the predictions of general relativity in a specific way would be a powerful hint that the cosmic speed limit was not always what it is today. It would force us to confront a universe where the most sacred constant in physics is not so constant after all, opening the door to a new and deeper theory of gravity that can accommodate such a profound change. The faint hum of these ancient waves could thus carry not just a message from the beginning of time, but a challenge to the very laws we use to interpret it. Now we arrive at a theory that offers perhaps the most radical and elegant alternative to the singular beginning of everything. Loop quantum gravity is a daring approach to the greatest problem in physics, unifying general relativity with quantum mechanics, and it proposes a universe that didn't begin with a bang but with a bounce. This framework takes the core idea of quantum theory seriously, applying it not just to matter and forces, but to the very fabric of spacetime itself. In this view, space isn't a smooth, continuous backdrop. It is woven from a network of tiny, one-dimensional loops, forming a fabric that is granular and discrete at the smallest possible scale, the Planck length. This fundamental graininess has a profound consequence. It prevents matter and energy from being compressed into an infinitely dense point. There is a limit, a point where gravity, instead of pulling everything into a singularity, becomes repulsive. This leads to the breathtaking concept of the quantum bounce. The standard Big Bang theory asks us to accept a moment of infinite density where the laws of physics break down a singularity. Loop quantum gravity removes this problem entirely. It suggests our universe was not born from nothing, but could be the latest cycle in an possibly eternal cosmic rhythm. Imagine the previous incarnation of our cosmos, a vast, cold universe contracting under its own gravity. As it shrinks, the density soars, but instead of collapsing into a singularity, the quantum repulsive force generated by the discrete nature of spacetime kicks in, like a cosmic spring reaching its maximum compression and then rebounding. The Big Bang is reimagined not as a creation event, but as this moment of transition, the big bounce where contraction stopped and our current phase of expansion began. This radical rethinking of the beginning has a direct and testable prediction for primordial gravitational waves. In the inflationary model, the waves are generated from quantum fluctuations stretched during a period of rapid expansion. But in the bounce scenario, the story is completely different. The universe that existed before the bounce would have had its own structure, its own history, and its own fluctuations. As that pre-bounce universe contracted, any existing gravitational waves or density perturbations would have been amplified and compressed, their wavelengths becoming shorter and their energy increasing. Then, during the bounce itself, the transition from contraction to expansion would have imprinted its own unique signature onto these waves. The resulting gravitational wave background would therefore not be a product of a brief period of inflation, but a relic that has been processed through the entire cosmic cycle of contraction and rebound. The signal from a loop quantum bounce would be unmistakable. The spectrum of these gravitational waves would be dramatically tilted compared to the inflationary prediction. At the very low frequencies that correspond to the largest scales in the universe, the signal would be strongly suppressed. It might even vanish altogether. However, at much higher frequencies, the waves would be significantly amplified, creating a powerful background hum in a part of the gravitational wave spectrum that is currently difficult for us to observe. This is a clear fork in the road for future experiments. If we build observatories capable of probing these high frequencies and find a strong, characteristic signal there, while simultaneously confirming the absence of the large-scale B-mode polarization in the cosmic microwave background that inflation predicts, it would be powerful, direct evidence for the bounce. It would mean that our universe has a history that stretches back beyond the moment we call the Big Bang, and that the fabric of spacetime is indeed woven from a web of tiny, vibrating loops, a quantum structure that saved the cosmos from its own collapse and set it on a new journey of expansion. Now we venture into the elegant and mind-bending world of string theory to explore a scenario that doesn't just explain the origin of our universe, but the origin of our very dimensions. This is the Brandenburger-Waffe scenario, a theory proposing that the three spacious dimensions we call home are not a fundamental given, but a cosmic accident, an evolutionary outcome that emerged from a more complete, higher dimensional beginning. To grasp this, we need to step into the strange reality of superstring theory, which suggests that the fundamental constituents of the universe are not point-like particles, but tiny, vibrating one-dimensional strings. For this theory to be mathematically consistent, it requires the universe to have more than the three spatial dimensions we experience typically. It demands 9 or 10. So where are these extra dimensions? The Brandenburger-Waffe scenario offers a compelling answer. In the fiery aftermath of the Big Bang, all of these spatial dimensions were compact, curled up into a space smaller than a single string. At this stage, the universe was a perfect, symmetric, higher dimensional point, but this state of perfection was unstable. As the universe began to expand, a critical process began. The theory posits that strings can wrap around compact dimensions, and these wound strings have a tremendous amount of energy stored in them, like rubber bands stretched around a tube. In 3 of the spatial dimensions, something remarkable happened. these wound strings managed to annihilate each other or unwind. This unwinding process released vast amounts of energy, which fueled the rapid preferential expansion of those three dimensions. They blew up to become the vast cosmic stage we see today. The other dimensions, however, failed to unwind. Their wound strings remained trapped, their energy locking them into a tightly curled, microscopic state, forever hidden from our perception. We don't see them not because they don't exist, but because they never got the chance to grow up. This dimensional unfolding was not a silent, gentle process. The annihilation of the wound strings and the violent, asymmetric expansion of only three dimensions would have been a cataclysmic event, shaking the very foundations of this new, emerging reality. The sudden release of energy and the dramatic change in the geometry of spacetime would have generated powerful gravitational waves rippling through the nascent cosmos. The spectrum of these waves, their distribution across different frequencies, would carry a specific and telling signature. Because the process was intrinsically tied to the fundamental scale of string theory, the string length and the size of the compact dimensions, the gravitational waves would have a characteristic peak frequency. This frequency would be a direct messenger telling us the energy scale at which string theory becomes important, a scale far beyond the reach of any particle accelerator we could ever build. Furthermore, the Brandenburger-Waffe model makes a second crucial prediction. As the three dimensions expanded, the remaining six dimensions stabilized at a specific fixed size. The vibrations within these hidden, compact spaces would also generate their own, much higher frequency gravitational waves. However, these waves would have wavelengths comparable to the size of those tiny dimensions, making them effectively invisible to our large-scale observatories. The overall gravitational wave background we could detect would therefore be a combination of the loud, lower-frequency signal from the great unwinding and expansion, and an undetectable whisper of high-frequency vibrations from the Calabi-Yau manifolds that house the extra dimensions. Finding a primordial gravitational wave signal with a specific, unexpected spectral shape could therefore be the first experimental hint that our reality is not just three-dimensional, but that our dimensions are the winners of an ancient cosmic lottery, with the losers still curled up, humming their own tiny tune just beyond the reach of our senses. But to truly stretch the limits of what we think is possible, we must consider a phase of matter so strange it inverts our normal expectations of reality, a state known as a ghost condensate. This isn't a condensate you could hold in your hand. It's a hypothetical phase that gravity itself could have entered in the extreme conditions of the early universe, a state where the very rules of Einstein's relativity are temporarily broken. At the heart of our modern physics is a sacred principle known as Lorentz invariance. This is the idea that the laws of physics are the same for all observers, no matter how fast they are moving or in what direction. It's the reason why the speed of light is constant, and it's a foundational pillar of Einstein's theory. But the ghost condensate theory dares to ask, what if that pillar wasn't always perfectly solid? What if, for a fleeting moment after the Big Bang, this symmetry was spontaneously broken? Picture the universe cooling from its initial fiery state. As it does, a new field, let's call it the ghost field, begins to condense, much like water vapor condensing into droplets, but this is no ordinary condensation. In this new phase, the ghost field acquires a non-zero value that is constant throughout both space and time. This might sound harmless, but its consequences are profound. This specific configuration gives the field a very strange property. It has a negative kinetic energy. In our everyday world, kinetic energy is always positive. It's the energy of motion. Something with negative kinetic energy turns the normal rules of physics on their head. It becomes a ghost, a substance that gravitates in the opposite way from normal matter. Instead of attracting, it can cause a gravitational repulsion, and its presence can fundamentally alter how perturbations and ripples behave in the fabric of spacetime. It is within this bizarre, transitory phase that a unique breed of gravitational waves could have been born. In standard physics, gravitational waves have two polarization states, and they travel exactly at the speed of light. But in a universe permeated by a ghost condensate, these rules are rewritten. The spontaneous breaking of Lorentz invariance introduces new, exotic polarization modes for gravitational waves. Some of these modes might not even travel at the speed of light. They could be dramatically slower or faster. Furthermore, the negative energy density of the condensate could have acted as an amplifier, taking tiny quantum fluctuations and magnifying them into powerful, classical gravitational waves in a way that is completely different from the standard inflationary mechanism. The resulting wave background would not have the clean, scale-invariant spectrum we often look for. Instead, it would carry a distinct, sharp peak at a specific frequency, a direct echo of the energy scale at which the ghost field condensed and Lorentz symmetry was momentarily lost. Detecting such a signal would be a monumental challenge, but its payoff would be nothing less than a revolution in fundamental physics. It would provide direct evidence that our most cherished symmetries are not absolute but can break under extreme conditions. It would force us to rewrite the textbook chapters on gravity and confront the existence of a form of energy that defies all our normal intuition. The ghost condensate is a window into a deeper layer of reality, suggesting that the universe's first moments were governed by laws even more strange and wonderful than we have yet imagined, and that their faint gravitational whisper might still be traveling through the cosmos, waiting for us to hear it. Now we move from the grand stages of cosmic drama to the subtle language of statistics, exploring a theory that looks for meaning not in the strength of the universe's first ripples, but in their hidden patterns. This is the non-Gaussianity connection theory, a concept that suggests the true secrets of creation are encrypted not in the volume of the primordial gravitational wave background, but in its intricate texture and the subtle correlations between its countless vibrations. To understand this, we need to step away from thinking about the average properties of these waves and instead consider their distribution, the statistical story they tell about how they were born. In the simplest, most elegant models of inflation, the quantum fluctuations that get stretched into gravitational waves are predicted to follow what's known as a Gaussian distribution. Imagine plotting the strength of these waves on a graph. A Gaussian or bell curve distribution would mean that most of the waves have a strength very close to the average, with fewer and fewer waves appearing as you move to extremely strong or extremely weak values. There are no unexpected correlations. Each fluctuation is essentially independent, a random event whose behavior doesn't influence the others. This clean, predictable pattern is the hallmark of a simple, single-field inflation model where the process was smooth, free from complicated interactions or sudden changes. It's the statistical fingerprint of a quiet, uncluttered birth. But the early universe may have been far more complex and turbulent than that simple picture allows. This is where non-Gaussianity enters the story. If we were to detect significant deviations from that perfect bell curve in the primordial gravitational wave background, it would be a monumental clue that the physics of inflation was rich with interactions. Non-Gaussianity is the statistical signature of coupling. It tells us that the fluctuations were not born in isolation. They were talking to each other, influencing each other, potentially mediated by other fields or by self-interactions within the inflated field itself. It's the difference between hearing a chorus of voices all singing independent, random notes and hearing a complex symphony where the melodies are intertwined, responding to and building upon one another. The specific type of non-Gaussianity, the precise way the distribution deviates from the perfect bell curve, acts as a detailed diagnostic tool, a cosmic fingerprint that points directly to the physics responsible. For instance, a certain skewness in the distribution could indicate that the process that generated the waves was inherently non-linear, that the fluctuations were so large that they began to interact with themselves as they were being stretched. Another pattern, a specific correlation between waves of different wavelengths, might be the smoking gun for the presence of additional quantum fields that were active during inflation, fields that coupled to the graviton or the inflaton and altered the statistics of the fluctuations. Each model of inflation, each proposed type of particle or interaction, predicts its own unique, subtle pattern of non-Gaussianity. Detecting that pattern would allow us to rule out vast swaths of simple models and zero in on the specific, complex physics that actually shaped our reality. This makes the search for non-Gaussianity in the gravitational wave background one of the most sensitive probes we can imagine. While measuring the overall strength and slope of the background tells us the energy scale of inflation, detecting its non-Gaussian statistics reveals the characters on the stage and the script they were following. It tells us about the interactions, the forces, and the particles that were present at that unimaginable energy, data we could never hope to recreate in any particle accelerator on Earth. The faint statistical correlations between these ancient ripples could be the key that unlocks the full story of inflation, moving us from knowing that it happened to understanding exactly how it happened and what other incredible physics was involved in the magnificent project of creation. But perhaps the most radical and mind-expanding possibility of all is that the ripples we are trying to detect are not just echoes from our universe's birth, but messages from entirely other universes. This is the multiverse imprint theory, a concept that pushes the boundaries of cosmology from studying a single cosmos to contemplating a vast, perhaps infinite, ensemble of realities, each with its own unique physical laws and constants. The most compelling version of this idea emerges from the theory of eternal inflation, which suggests that our universe is just one bubble in a gigantic, ever-expanding cosmic foam. In this picture, the vacuum energy that drove our inflation is not unique. It is just one value in a vast landscape of possibilities. Elsewhere in the meta-universe, other bubbles are continuously nucleating, each with a different vacuum energy, each inflating to become a full-fledged universe with its own Big Bang and potentially its own laws of physics. In this frothing multiverse, these bubble universes are not forever isolated. As they expand at nearly the speed of light within the wider inflationary background, they can occasionally collide with one another. The boundary where two such bubble universes meet would be a cosmic event of unimaginable scale and energy. The collision would not be a soft merging. It would be a violent impact as two distinct regions of spacetime, each with potentially different fundamental properties, slam into each other. This colossal event would send a tremendously powerful spherical shockwave racing through the interior of both universes. This shockwave would not be made of sound or light. It would be a distortion in the very geometry of space, a powerful, coherent gravitational wave that would imprint itself onto the cosmic microwave background radiation within each colliding universe. The signature of such an event would be unmistakable and could not be easily explained by any internal process within a single universe. As this gravitational wave shock front passes through the early plasma of our universe, it would create a very specific circular pattern of hot and cold spots in the CMB, a kind of bullseye or concentric ring signature that stands out starkly against the random Gaussian fluctuations from standard inflation. The precise temperature profile and polarization pattern within that ring would carry encoded information about the collision itself, the energy of the impact, the angle at which the other universe hit us, and perhaps even clues about the physical laws that govern that foreign cosmos. Finding such a pattern would be the first direct observational evidence that our universe is not alone, that we are part of a much grander multiverse. The implications of such a discovery would fundamentally reshape our understanding of reality and our place within it. It would bring the anthropic principle, a once purely philosophical idea, into the realm of testable science. This principle suggests that the fundamental constants of our universe appear finely tuned for life not because of divine purpose, but simply because we exist in one of the rare universes within a vast multiverse where the constants accidentally allow for stars, planets, and conscious observers. A confirmed bubble collision would provide a physical mechanism for this selection effect, offering a naturalistic explanation for the apparent fine-tuning we observe. It would mean that the laws of physics we hold as universal and immutable might merely be the local bylaws of our cosmic neighborhood, with completely different rules operating just beyond the boundary of our observable universe. The faint gravitational ripples we are searching for could therefore be the first hard evidence that reality is far stranger and more magnificent than we ever dared to dream, a single note in an infinite cosmic symphony. Yet for all the cosmic violence and high-energy physics we've explored, one of the most profound connections lies in a puzzle that seems to question the very nature of reality itself: the black hole information paradox. This isn't just a problem about black holes, it's a crisis at the heart of our understanding of physics, a direct conflict between the two pillars of modern science, Einstein's general relativity and quantum mechanics. And remarkably, the key to resolving this decades-old paradox might be encoded in the universe's very first gravitational whispers. To understand the paradox, we need to start with a seemingly simple question: what happens to information when it falls into a black hole? In our everyday world, information is never truly lost. If you burn a book, the ash and smoke still contain the complete information about that book. In principle, with a perfect understanding of physics, you could reverse the process and reconstruct it. This principle of information conservation is a bedrock of quantum mechanics, but black holes, according to Einstein's theory, present a terrifying problem. They have an event horizon, a point of no return from which not even light can escape. If you throw that same book into a black hole, it seems the information contained within it is lost forever to our universe, violating a fundamental quantum rule. The crisis deepens when we consider Stephen Hawking's groundbreaking discovery that black holes aren't completely black. They slowly evaporate by emitting radiation. This Hawking radiation, however, is thermal, it's random heat radiation. It carries no information about what fell into the black hole. So, if a black hole eventually evaporates completely, leaving behind nothing but this featureless radiation, what happened to the information in the book? It appears to be erased from existence, which quantum mechanics says is impossible. This is the information paradox, the irreconcilable clash between the smooth, deterministic predictions of general relativity and the strict information preservation demanded by quantum theory. For decades, physicists have proposed solutions, and one of the most promising is the idea of quantum hair. The concept suggests that information isn't actually lost inside the black hole. It's somehow imprinted onto the event horizon itself, subtly altering its gravitational field in a way that encodes the information about what fell in. These faint imprints are the quantum hair, and as the black hole evaporates via Hawking radiation, this information is slowly and subtly leaked back out into the universe, encoded in the correlations within the radiation. The information is never truly lost, it's just incredibly scrambled and difficult to decode. This is where primordial gravitational waves enter the story in a breathtaking way. The process of inflation, which stretched quantum fluctuations into cosmic-scale gravitational waves, is fundamentally a quantum gravitational process. Those initial fluctuations were not random noise, they were a specific quantum state, a particular arrangement of information about the universe's initial conditions. When inflation stretched these fluctuations, it didn't erase that quantum information. It fossilized it, translating a quantum state into a classical, permanent imprint on the geometry of the universe, the gravitational wave background. This process is a potential blueprint for how information can be preserved during a seemingly destructive event, much like information might be preserved at a black hole's horizon. The primordial gravitational wave background could therefore be the ultimate test case. By studying its detailed statistical properties, its specific pattern of correlations and amplitudes, we are effectively studying a fossilized quantum state from the dawn of time. If we can show that the information in that initial quantum state was perfectly preserved and translated into the classical gravitational wave signal we see today, it would provide a powerful analog and a huge boost for the quantum Hare solution to the paradox. It would demonstrate that a quantum state can be imprinted onto the fabric of spacetime without being lost, offering a tangible example from cosmology that could guide our understanding of the black hole information problem. The faint ripples from the beginning of everything might carry the answer to one of the most enduring mysteries in physics, revealing a universe that preserves its history not in books or atoms, but in the very curvature of spacetime itself. For decades, our ability to listen to the cosmos has been constrained, limited to a specific, narrow band of the gravitational wave spectrum, like trying to understand an entire symphony by only hearing the piccolos. Ground-based detectors like LIGO and Virgo are exquisitely tuned to hear the high-frequency crescendos of the universe, the final, frantic moments of stellar mass black holes and neutron stars colliding. But the primordial gravitational wave background is a different kind of music altogether. It's not a sudden, transient crash of cymbals. It's a deep, pervasive, low-frequency hum, the foundational bass note of existence that has been resonating for over 13 billion years. To finally hear this ancient melody, we need a new generation of instruments, colossal observatories designed to listen to the quietest and oldest sounds in the universe. This final theory isn't about the origin of the waves themselves, but about our future quest to capture them and how that detection, or even its absence, will fundamentally rewrite the story of our cosmic beginning. The first and perhaps most anticipated of these new instruments is the Laser Interferometer Space Antenna, or LISA. This is not just an upgrade, it's a complete paradigm shift. Instead of building detectors on the shaky, noisy surface of Earth, LISA will consist of 3 spacecraft flying in a perfect triangular formation, trailing behind Earth in its orbit around the Sun. Each side of this triangle will be 2.5 million kilometers long, a ruler of almost unimaginable precision floating in the void. By firing lasers between these spacecraft and measuring the microscopic changes in the distance between them caused by a passing gravitational wave, LISA will achieve a sensitivity that is simply impossible on Earth, free from the rumble of earthquakes and the din of human activity. LISA is designed to listen to the low-frequency gravitational wave band, the sweet spot where we expect to hear the combined chorus of millions of binary systems within our own galaxy. The mergers of massive black holes at the hearts of distant galaxies, and crucially, the steady hum of a primordial gravitational wave background if it is strong enough. But what if the primordial signal is even fainter or lies at a different frequency than we expect? This is where the next stage of terrestrial technology comes in, the Einstein telescope and cosmic explorer. These are envisioned as third-generation ground-based observatories, but that label undersells their ambition. The Einstein telescope is designed to be an underground, triangular-shaped detector with arms 10 kilometers long. Its subterranean location and cryogenically cooled components dramatically reducing seismic and thermal noise. Cosmic Explorer, a potential US-based project, envisions arm lengths of 40 kilometers, an enormous scale that would push the sensitivity of LIGO-style interferometers to their absolute physical limits. While these beasts will still probe higher frequencies than LISA, their incredible sensitivity will allow them to search for the high-frequency tail end of the primordial background. Furthermore, by observing for years, they can look for the distinct, unchanging statistical signature of this background noise buried beneath the individual chirps of black hole mergers. If the primordial waves are within their frequency band, even if incredibly faint, these observatories could tease them out. The real power, however, won't come from any single observatory, but from a coordinated network, a gravitational wave astronomy revolution spanning the entire spectrum. Imagine Lisa listening to the low hum while the Einstein telescope and cosmic explorer scour the mid to high frequencies all simultaneously. This multi-band approach is our ultimate strategy. Each theory of the universe's origin makes a specific prediction about the shape or spectrum of the primordial gravitational wave background across different frequencies. For instance, the signal from a first-order phase transition would produce a peaked spectrum, a distinct mountain on a graph that would appear at a specific frequency determined by the temperature of the universe when it occurred. The signal from cosmic strings, however, would produce a much flatter spectrum, a persistent roar across a huge range of frequencies. By mapping the intensity of the background from the lowest frequencies, Lisa can hear all the way up to the highest frequencies Cosmic Explorer can detect. We will be able to match the observed curve to these theoretical predictions like a key fitting a lock. The shape of that curve will be the ultimate cosmic fingerprint, pointing directly to the physical process that created it. The implications of a clear detection are almost beyond comprehension. Finding a strong, scale-invariant signal would be the ultimate validation of simple, single-field inflation, confirming that our universe began with a smooth, exponential stretch of the quantum vacuum. Detecting a sharp peak would be a smoking gun for a violent cosmic phase transition, perhaps even the one responsible for generating the matter-antimatter asymmetry. A flat spectrum would point us toward a network of cosmic strings, ancient defects formed as the fundamental forces froze into their current form. Each detection would not just be a new data point, it would be a direct message from the first fraction of a second after the Big Bang, an era previously thought to be permanently inaccessible to science. We would move from theoretical speculation to concrete knowledge about the birth of everything. Yet, perhaps equally profound would be a continued, definitive non-detection. If we build these magnificent observatories and after years of listening, hear nothing but silence where we expected a primordial hum, it would force a radical rethink of our cosmic origins. A null result would effectively rule out many of the more energetic and violent early universe scenarios, including strong versions of inflation and certain types of phase transitions. It would lend powerful support to alternative theories like the ekpyrotic universe, which predicts an incredibly faint gravitational wave signal, or other models where the universe's beginning was far more gentle and smooth than we currently imagine. The absence of a signal is itself a signal, a loud and clear message that our current favorite theories are wrong, and that we must venture down new, perhaps even more exotic, paths to understand where we came from. This future search, this grand experiment played out across the solar system and deep within the Earth, is our best and only chance to answer the oldest questions humanity has ever asked by listening for the faintest echo of the very first moment. From the silent tremors of quantum foam to the thunderous crashes of colliding bubble universes, the incredible diversity of these 30 theories paints a picture of a cosmic genesis far richer and more complex than we ever could have imagined. We've journeyed through possibilities where the universe was born from a bounce, not a bang, where its very dimensions were forged in the unwinding of cosmic strings, and where the faintest ripples in space-time could finally reveal the identity of dark matter or resolve the paradox of our own existence. Each theory, whether grounded in established physics or soaring at the edge of speculation, offers a unique window into that first fraction of a second, a testament to humanity's relentless drive to understand its origins. What's truly breathtaking is that we are no longer limited to pure thought experiments. We are standing at the dawn of a new era of observational science. Gravitational wave astronomy is providing us with the tools to finally listen to the universe's opening notes. With current observatories like LIGO and Virgo, and the future promise of LISA, the Einstein telescope, and Cosmic Explorer, we are building a galactic-scale hearing aid, an interconnected network of instruments that will scan the entire gravitational wave spectrum. This isn't just about adding another sense to our astronomical toolkit. It's about tuning into a channel that has been broadcasting since the beginning of time itself. A channel that carries information from a time before light, from energies beyond our reach, and from processes that shape the very laws of nature. The search for these primordial ripples is more than a technical challenge. It is one of the most profound journeys of discovery we can undertake. It connects the impossibly small world of quantum mechanics with the grandest scale of the cosmos, bridging the gap between the behavior of subatomic particles and the fate of the entire universe. Whether we detect a loud, clear signal or are met with a telling silence, the result will force a revolution in our understanding. It will either confirm our most cherished theories or, perhaps more excitingly, tear up the textbooks and send us back to the drawing board, armed with new, unexpected data from the dawn of creation. So stay curious. Let the sheer wonder of these ideas ignite your imagination. The questions we've explored today: how did it all begin? What is the true nature of spacetime? Are we part of a larger multiverse? Are the most fundamental questions we can ask. They connect us to every human who has ever looked up at the night sky in awe and wondered. The answers are written in the subtle vibrations of space-time, and for the first time in history, we are learning how to read them. The universe's first whisper is still traveling, and we are finally, patiently learning how to listen.